Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we will look at integration. So integration is basically anti-differentiation, the opposite of differentiation. When you see something like the integral, that's what this symbol means, the integral of x squared, we're saying what function do you differentiate to get x squared? So integration and differentiation undo each other just like the operations of multiplication and division or addition and subtraction. So when we are integrating, performing an integral, finding an antiderivative that is, you'll see symbols like dx. So that basically for our purposes just tells us the variable with respect to which we are integrating. So integration is the opposite of differentiation. Now, when we differentiate x to the power of something, we times by the power and decrease the power by 1. So when we're integrating, we do the opposite. If you integrate x to the power of something, you increase the power by 1 and divide by the new power. And similarly for sine and cos, we do the opposite of differentiating. Just note the derivative of sine is cos, but the integral of sine is negative cos. And similarly, the derivative of cos is negative sine, but the integral of cos is positive sine. So just like for differentiation, e to the power, the e and the power stay. This last rule tells us that what we learned about linear combinations also holds for integration. If you're integrating a constant times a function, you can just integrate the function and times by the constant. And this rule also allows us to go term by term. If we're integrating lots of terms, we just integrate the first term, then the second term, and so on. Okay, let's actually get into it, so hopefully this makes a bit more sense. So let's go through and find the integral of x squared dx. So we're going to use this rule here. So we're going to simply increase the power by 1 and divide by this new power of 3. The reason the integral of x squared is x cubed on 3 is because if we differentiate this, we get x squared. But here's the thing, there are actually infinitely many functions we could differentiate to get x squared. If you differentiate x cubed on 3, you get x squared. If you differentiate x cubed on 3 plus 1, you get x squared. If you differentiate x cubed on 3 plus 200, you get x squared. So what we do is usually write a plus c. This c means constant. X cubed on 3 plus any constant. If you differentiate any function of this form, you'll get x squared. That's what all of the plus c's here are about. All right, let's integrate this function here. Again, we're using the power rule. So it might be easiest for us first to write everything as powers of x. So cube root of x to the power of 4 is x to the power of 4 over 3, minus 1 on x squared is x to the power of negative 2, and then we've got plus 2. Again, the dx tells us we're integrating with respect to x. Just like in here we had, a, x, and b, the x just allows us to know that this is the one we're integrating with respect to, and a and b are treated as constants. Okay, let's go ahead and do this. We're going to use the power rule. So for x to the negative 4 over 3, what we're going to do is increase the power by 1. So 4 over 3 plus 1 is 7 over 3. We need to divide by that new power, 7 over 3. But just note that dividing by 7 over 3 is the same as timesing by 3 over 7. So that's what it will look like. What about the integral of negative x to the minus 2? So what we're going to do is we're going to increase the power by 1 and divide by the new power. Of course, the two negatives here cancel each other out and they end up making a positive. So it's going to be plus x to the power of minus 1. Now you'll often be asked to write it with a positive power, so I'll just change that to 1 over x. Now when we differentiate, constants disappear. But when we integrate a constant, it doesn't. This is 2x to the power of 0. So what we have to do is we have to increase the power by 1 and divide by new power. Of course, you don't really need to write the divide 1. This is just 2x. So that whenever you integrate a constant, it's just that constant times the variable. So integral of 3 is 3x, integral of 4 is 4x, integral of negative 7 is negative 7x, and so on. Now when we're integrating, don't forget to add the c, because if I differentiate this function, I get this as my answer, but any constant wouldn't change that. All right, let's go ahead and do this one here. So for the integral of e to the negative x, we're using this rule here. Here a is negative 1, b is 0. So the integral of e to the negative x is going to be e to the negative x divided by a was negative 1. Of course, I can just write that as negative e to the negative x. So the integral of 2 cos x on 2. So here we kind of have a being our half, because x over 2 is the same as a half. So the integral will be 2. I'll leave the 2 alone. So I'm going to change the cos now to sine. Now you keep the argument, what's in the bracket, the same, but we need to divide by a, which we decided was half. So once again, I'm going to simplify that. 2 divided by a half is 4, so this becomes plus 4 sine x on 2, and I have to add the c. So once again, if you are integrating many terms, just integrate term by term. Now, something like e to the x squared. So a lot of people might think, okay, cool. So we're going to keep the e to the same power, and then we just divide by the derivative of that power. That actually doesn't work, because if you differentiate e to the x squared over 2x, you need to use the quotient rule. In fact, this one doesn't have any elementary functions. We can't easily find a function whose derivative is equal to this. So we need to use numerical methods that we'll learn about in a later lesson. All right, let's now look at some integrals involving logs. So we know that when we differentiate log of a function, we put the function on the bottom, its derivative on top. Now we're just going the other way. So if you have an integral with function on the bottom, its derivative on top, it's just log of that function. Notice we need to put it in absolute value brackets, because logs can only take positive values for their arguments, whereas this function might be able to take more values. Once again, we need to add the c. So let's go ahead and integrate 4 over 5x. So we can actually rewrite this as 4 over 5 times the integral of 1 over x dx. So you can take constants out the front of the integral sign because of that linear combination rule on the first slide. You can't, however, take a variable. You can never take an x out the front here, but taking out a constant is fine. Now, the integral of 1 on x is just natural log of x. So the final answer is 4 over 5 natural log, and we write the absolute value of x because this has to be positive. All right, what's the integral of 3 over x minus 1? So you'll see when we do a lot of integration, a lot of the time we just rewrite the expression so they're easy to integrate. We can again take 3 outside the front. So now we've got a situation with a function on the bottom and its derivative on top. So when we have such a situation, we'll just put the constant out the front. It's natural log of the function on the bottom. All right, what about this one here? Well, this is actually almost in this form. See, the derivative of x squared minus 6x is actually 2x minus 6. That's what I really want on the top. So what can I do? Well, I can actually rewrite this. I can take out a factor of 2. Note that 4x minus 12 is just 2 times this. So if I rewrite it like this, it's going to be in the right form. Now I have a situation where I have a function on the bottom and its derivative on top. Notice that these are equivalent because 2 times 2x minus 6 equals that. So the answer when you have a function on the bottom and its derivative on top, it's just, we'll put any constants out the front, natural log of the absolute value of whatever's on the bottom plus c. So this one here actually can be written in this form. It just takes a bit more work. So we have x plus 3 over x plus 5. What we want to do, what we really would love, is if the top was x plus 5 as well. This is what we want it to look like, because x plus 5 over x plus 5 is just 1. But of course these two aren't the same thing. So what I need to do is I need to subtract 2 to make them the same thing. See, these two are the same. X plus 5 minus 2 does equal x plus 3. So this here is just 1, as I said before. So this is the integral of 1. Integral of 1 is x. And this is just going to be negative 2 times the natural log of x plus 5. And we can't forget to write the c. And then we're done. All right, let's just look quickly at an initial value problem. So here we are asked to find capital F of x. Note that means the antiderivative of fx. Now we're given here what's called an initial value. See, in all the previous examples we've just written function plus c. But if you have an initial value, you can find c. So if I want to find capital F of x, it's the antiderivative of that. I just use integration. So it is going to be the integral of x to the power of a half. It's easier to write it as a power. Okay, so how do I integrate that? Well, the rule for powers of x, you increase the power by 1 and you divide by the new power. But dividing by 3 over 2 is the same as timesing by 2 over 3. So we again need to add plus c, but because we have our initial value, we can find what c is. So because f of 1 equals 7, what that means is I can substitute x for 1, so 1 to the power of 3 over 2 is just 1, plus c, and that must equal 7. So we can see clearly c will have to be 6 1/3 or 19 over 3. So that means that the antiderivative, it was 2x to the power of 3 over 2 over 3. That part was right, but now we found c. We can write that as well. All right, thank you so much for tuning into this video. This has been the luckiest maths teacher in the world. Have a great day.